Today's lesson is all about bond polarity and electronegativity, and you can see we have three questions that we're trying to answer. First, we're trying to relate the term bond polarity to electronegativity, which is another periodic trend we're going to look for. The second question, we'd also like to learn what is the periodic trend for electronegativity on the periodic table. And finally, we want to understand how does bond polarity affect the physical properties of a substance. So the concept of bond polarity is that when atoms bond, the nuclei of each atom attracts to the electrons that are being shared in between those two atoms. And so those shared electrons are the bonding electrons. And how evenly or unevenly the electrons are shared determines whether or not the bond is polar or nonpolar. So if we have a nonpolar bond, what that means is that the electrons are shared equally. So you have two atoms with nuclei that have approximately equal strengths. Their effective nuclear charges is about the same. So the electrons in the middle are shared evenly. Think of it, for instance, like you're watching a movie and you're sharing a blanket with someone, and both of you are about the same, let's say, level of coldness. So if you're the same level of coldness, you need that blanket about the same amount. That would be an analogy for nonpolar covalent bonding. For polar covalent bonding, that's when electrons that are being shared to form that covalent bond are not shared equally. So one nucleus has a much greater attraction to the electrons that are being shared than the other atom. So to go back to that blanket analogy, if one person's really cold, another person's really warm, then the really warm person really doesn't need to hold on to that blanket, and they let the other person take more of the blanket. And that's what happens in a polar covalent bond. Let's take a look at a picture that represents that. And in terms of colors, these greens and yellows represent equal electron sharing. So this is a fluorine atom here, this is a fluorine atom here, and the electrons they're sharing in the middle are being shared equally. On the other hand, we have hydrofluoric acid, and hydrogen is over on the left-hand side, fluorine's on the right side. As you might remember, fluorine has a really high effective nuclear charge, and so it has a great ability to attract electrons. So when hydrogen and fluorine bond, the fluorine is going to take more of the electron density from that bond than the hydrogen will. So in a sense, what we end up with is the fluorine area being slightly more negative and the hydrogen being slightly positive. These colors represent that. So anytime you see in our book this red as a part of one of these electron density images, that means more electronegative, more of the charge. And then on the other side, you see that blue or purple color, that means that there's much less of the electron density being shared by that atom. So one of the terms I just started to throw out there is electronegativity, and it describes the ability of an atom to attract electrons to itself, and we use this term usually in reference to the formation of a covalent bond. So elements that attract electrons to a high degree have high electronegativities, and those elements that don't attract electrons aggressively have low electronegativities. And this lends itself to a periodic trend because this is all related to shape and effective nuclear charge, atomic radius, all the things we learned about last chapter. And so let's take a look at this. If we switch over to this view, take a look at the bottom here. You can see that the electronegativity increases as the effective nuclear charge increases, and electronegativity also increases as the atomic radius decreases. So that's the trend. This is very similar to ionization energy trend. One of the big differences, though, that you'd notice is that group 18, which is the noble gases, is not listed here in these electronegativities in this table. By the way, the electronegativity chart basically runs from a 0 range up to 4 for each element. So fluorine is the highest at 4, and the smallest is francium. I believe it's at a 0.7. To answer our first question that we had, which was about the relationship between electronegativity and bond polarity, what we can say is that bond polarity can be estimated if we subtract the electronegativities of the bonding atoms. So looking back at this periodic table, if we go find this in our book and we look up the elements that are formed or coming together in one covalent bond or one bond, we could take these digits, these numbers, subtract them, and the difference gives us an estimation of electronegativity. So, for instance, if we were to look up the elements phosphorus and oxygen, and we take the absolute value of those differences, so this number is always positive, we would get an estimation of the difference in electronegativity and the bond polarity. If you look at the table I created at the bottom, this table does not appear in your book, so you're not going to see a lot of homework questions about what's the difference, what type of bond is it based on the difference. But here's what you can see. What we call a nonpolar covalent bond, where electrons are shared equally, will have an electronegativity difference that's less than 0.4. And polar covalent bonds have a difference of 0.4 to 1.7, and then ionic bonds would have a difference in these electronegativities of 1.7. In other words, there's so much of a disparity between the ability to attract electrons in one atom compared to the ability to attract electrons in the other, that one atom completely removes electrons from the other. So metals and nonmetals normally have a difference in electronegativity of 1.7 or higher. Something that I point out here is that there is no clear line of separation between these different types of bonds. And there's a page in your book towards the end of this section that's all about this. So even though we've set up a little scale here to describe and predict what type of bond we're talking about, this really isn't clearly distinguished. It's not black and white. Bonds can have character of nonpolar and polar, polar and ionic, etc. Taking a look at this table, one of the things that I want to point out here is you can see that as the electronegativity difference in the table is greater, you can see that there's a greater differentiation in the colors. So HF, the H and the F have a difference of 1.9, fluorine being the highest at 4.0, and so it's very electronegative. It's got a lot of the electron density. Hydrogen is very low density in terms of its electron cloud. As this difference in electronegativity weakens, you can see that the color distinction weakens also. And so HBr over here is even weaker. You don't see the red anymore. It's not as extreme. And HI, you only see green and yellow colors. The difference is almost nonpolar. So it's important to realize that you can have different degrees of polarity within a bond, where there's a very large difference or there might not be much of a difference at all. It's a little bit hard to see. Let's see if I can turn that down for you. There we go. So a term that comes up is dipole moment, and it can be calculated as a number, but basically a dipole moment refers to that degree of difference in the polarity or the difference in electronegativity of those bonds. So a large dipole moment means that you have a very electronegative atom with a very low electronegativity atom, and that would mean that there's a great difference in the electron density. This is going to impact bonding and some other properties. There are a couple ways that you'll see dipole moments represented or a polar bond being represented, and you can see them at the top of the page. The first one is this arrow with a little plus sign on one side. The arrow is drawn in the direction of the electron density that's higher, or the more electronegative atom, we could say. And then the plus sign is near the atom that has less electronegativity. It has less of the electron density, so it's effectively slightly positive. Over to the right, you can see some delta symbols. Those are lowercase deltas, and that's another way of representing the polarity or the dipole moment. So our partially positive hydrogen with low electron density and the partially negative fluorine, with a high electron density. There are some applications of bond polarity. and this is our third question that we're covering. And we'll get more into these later, but I just wanted to introduce them to you this section since we're talking about it. And that is polarity and dipole moments affect solubility. They also affect freezing point. And so in general, what we'd say is like dissolves like. Polar molecules dissolve polar molecules, nonpolar molecules dissolve nonpolar molecules. Ionic compounds prefer polar molecules because they're also positive negative. So there's a pretty good attraction there. This kind of interaction affects the shapes of proteins. So when proteins start to go from a primary structure to a secondary structure to a tertiary structure, quaternary structure, then they start to fold in on each other. And how they're held together is by all these little attractive forces. It is also then we're saying that polar molecules and nonpolar molecules don't mix well. And so something with a dipole moment doesn't go well with something that does not have a dipole moment. And finally, if we take a look at my little representation of water here, and this happens in liquid water, it happens in ice, but in general what we can say is that the slightly positive parts of water attract to the more negative parts of water. So you'll see that the hydrogen of one molecule attracts to the oxygen of another. This ends up playing out in an ice crystal, but it's also impacted even in the interactions within liquid water. So in summary, depending on the difference in electronegativity, a bond or molecule may be nonpolar covalent, polar covalent, or ionic in character. So we can use the electronegativity table to help us make a prediction on that. We can also say that as an element becomes less metallic, meaning it takes on a higher ionization energy, that the electronegativity also increases. Remember that the exception there is the noble gases because they don't bond with others typically, so we don't really measure their electronegativities. Finally, polar covalent molecules have a dipole moment, and that affects their properties such as solubility and miscibility. Miscibility, by the way, is mixing of liquids, and then freezing melting point. So this has been your overview of 8.4. It's a pretty tricky little section in the book, but it helps you to understand some things later on.